Our next type of equation that we're going to look at are related to implicit differentiation. For example, let me just grab an equation at random here. We have x squared plus xy plus y squared equals 9. And what you typically would do in, say, a calculus class is you would take the implicit derivative of both sides. Say, so I'll do d over dx of x squared plus xy plus y squared. And that's the same as d over dx of 9. Now the 9, of course, becomes a 0. But on the left, you take the derivative with respect to x, so the x squared becomes 2x. Here you have xy, you've got to use a product rule on it. So I'll start with the derivative of x would be 1. You would leave y alone, but then you would leave x alone and then take the derivative of y. I'll call it y prime. And finally, to do y squared, you take the 2 down to become 2y. But then you had to attach y prime because of the chain rule. So this is typically something you would do. I'm going to switch my notation to 2x plus y plus x times dy over dx. Instead of y prime, I'm going to use dy over dx plus 2y times dy over dx. And that's equal to 0. Now, like we've done with so many other things, I'm going to multiply everything through by dx. So I will get 2x dx plus y dx plus x dy plus 2y dy, because the dx's in the last two pieces canceled out. And that's equal to 0. Now I'll collect some things. I'll have 2x plus y dx plus x plus 2y dy. And I just noticed I made a mistake up here. That's a dy. And that's equal to 0. These are the type of equations we're going to be looking at, starting with this and trying to work our way backwards to get the solution. So let me show you the steps that we're going to use, and then I'll talk about partial derivatives and other things that come into play. But for the time being, we are going to work with equations that look like this. Some sort of a function m times dx plus some sort of a function n times dy equal to 0. And that's exactly what we have here. What we're going to insist upon is that when I take the derivative of m, or the derivative of n, they end up being equal. I'll show you what I mean. M in this case is equal to 2x plus y. And now, I am going to take the derivative of m with respect to y. So m sub y equals. Now, if I am taking the derivative with respect to y, I am acting like x is a constant and y is the variable. If that's the case, then, since x is a constant for this type of derivative, the derivative of 2x will be 0, the derivative of y will be 1. Similarly, I'm going to match n up with the stuff before the dy. That equals x plus 2y. And then this time I'm going to do n sub x. That means I'm going to take the derivative with respect to x alone. Means that y is going to be treated like a constant. That means 2y will disappear. The derivative of x with respect to x is 1. Now, if I have that, here's the technique I'm going to use to get us back to the answer. So let me go start here, example 1. I'm going to have you solve the equation that I ended up with before, 2x plus y dx plus x plus 2y dy, and that's equal to 0. Now, we saw that I took the derivative of an expression. I took the derivative of this thing here in order to arrive at what we have. So I want to go backwards. What that means is I am going to integrate each piece of this. So I'm going to integrate 2x plus y dx. The dx tells me we're going to integrate with respect to x. That means you're going to think of y as a constant. So for instance, this piece, this 2x, will become x squared. But the y portion, it's like a constant. So if it were just a 1, for instance, or a 2, when you integrate it, it becomes 2x. So just like that, we're going to become x times y. Now there's one last piece. Typically, you would have a constant after you integrate. However, since we're dealing with two variables, when I take derivatives with respect to x, things that have y in them disappear. So when I integrate, I have to make sure that I include any possible y's, solo y's, that might have occurred. So I'm going to put a little cy here to indicate that this thing here is going to be a constant, but it's probably going to be a function of just y alone. Now I'm going to do the same thing with the other piece. Here, I have x plus 2y dy, and the same deal as before. This is dy, not dx. So treat x as a constant this time, so x will become xy. Y, of course, is what we're integrating with respect to, so I'll get y squared. And just like before, when I integrate with respect to y, I may have a constant that involves only x's, because when you differentiate, those disappear if you're differentiating with respect to y. Now, I want you to look at these two things here. If you look, they have something in agreement, xy. And if you also look, I have an x squared and I have a y squared over here. The constants I was talking about here, the cx, is this x squared. That is a function of x squared alone, of x alone. If I differentiate this with respect to y, it does turn into 0. Similarly, this c sub y here, you can find it as y squared. So what we have here is we have a basic function, this xy, that has two variables in it. It's not a function of either x or y alone. It's a function of both of them. So the way I write my answer for these things is I'll take this function of xy, of x and y, plus I want my c sub x, so I'll have x squared. Then I want my c sub y, or the y squared, and that's equal to a constant. And I'll show you why that is. So this is what this would be the solution to the problem that I gave you to do. And if you'll notice, if we go all the way back to the original problem, right here, this is the answer. We just didn't know it was 9. I would know it was 9 on the other side if I had been given an initial piece of information, an initial value. I'd be able to get that c, that equal to 9 back. But that's the idea. Let me show you the idea in more detail. One of the things, if you've had Calculus 3, this will be review. If you've had Calculus 2 and not Calculus 3, you probably have not seen this before, dealing with multiple variables. But when you do that, let me just show you for a minute. When I did d over dx of x squared plus xy plus y squared equals to d over dx of the constant, I could have multiplied through by dx first. Now, it really doesn't matter. Any derivative of c is going to be 0. Over here, though, instead of having y primes, this is what's going to happen. When I take this is the differential of this expression. So when I take the differential of x squared, I'll end up with 2x, and then I attach a dx. Then when I do xy, I'll take the derivative of x first, just like I would before. So I'll get 1 times y, but I will attach a dx since the derivative was with respect to x. Similarly, I will leave x alone, multiply by the derivative of y with respect to y is equal to 1 times dy. And I'll finish it off with 2y dy, and that equals 0. Let me combine my dx's, and I'll have 2x plus y dx plus x plus 2y dy, and that's equal to 0. So this yields exactly the same thing I had before, but this time I differentiate or multiply through the dx to begin with. So right here, what we have then is the differential of this stuff. And so the way we write it is like this. Remember, this stuff here was when I took the derivative with respect to x. So let me use some notation. I am going to let f of x sub x comma y equal x squared plus xy plus y squared. Then I'm going to define a notation that looks like this. A curly d of f, curly d of x. This is the partial derivative of the function with respect to only x. So you'll treat y as a constant when you take this derivative. So I'll get 2x plus, now when I take the derivative with respect to x, this will become a 1, and the y is unaffected. This is like a constant times x. So you'll be left with just the y portion, and then the y squared disappears. Similarly, I can do the same thing for y. Notice the curly d's. That's not the same as the regular d's. That curly d is specifically meant to deal with partial derivatives. You're only dealing with one variable, and that's the variable down here. So now I'm going to reverse. X is like a constant, and y is the variable. So when you take the derivative of y with respect to y, the x disappear. And so this part right here will be x times 1, or just x, and then y squared will become 2y. And you can see these are exactly what I have here and here. Then to define the differential with respect, well, just differential, it takes into account all the variables, is given by this formula. The partial of f with respect to x times dx, and that's a regular d, plus the partial of f with respect to y dy. And let me go ahead and fill those in. I have 2x plus y times dx plus x plus 2y times dy. And that's exactly the expression I had before. So this is the game we're going to play here. This guy right here is the type of equation I'm going to be dealing with. So let me show you what happens then. If I go back to this equation, d of f of xy is equal to the partial of f with respect to x times dx plus the partial of f with respect to y of dy. To solve this, we're going to be trying to figure out what f was. So anytime you go to solve a differential equation, an integration is going to come in. I'm going to integrate both sides of this equation. As before, the integral and the d cancel out, and we get f of xy. Now over here, I'm going to break this up into two integrals. The partial of f with respect to x dx plus the integral of the partial of y, the partial of f with respect to y dy. And what happens, this was the derivative with respect to x. If you integrate the derivative with respect to x, you'll end up with the original function again. But don't forget, you'll get some constant that may have y values in it. And over here too, you're going to get f of xy again, plus a constant with respect to x. Now, this is not that big of a deal. It may say, why is f of x equal to 2 of these? Well, remember, the equation we're trying to solve was equal to 0. That means it's going to be a constant. And if I wanted to, then if I got 2 of these things, I could simply divide by 2, and on the other side I would have a constant, and the constant would swallow up that division by 2. So this is the game plan of what we are going to do. Now, do I need to define them? I will. Let me just, for 1 second, let me define what that thing is. If I have a function, or the partial of f with respect to x, for example, is a derivative like you're used to from Calculus 1, except the only variable that is changing possibly is the x. The y is held constant. And you can see right here that if I had not had these y's here, this is the exact same definition of a derivative in one variable. It's just that the x's are moving and the y's are staying constant. That's what I've been saying the whole time. If I want to do the partial with respect to y, then the x's would stay constant, but I would have a y plus h here. Well, let's get into some examples to see how this stuff all works. Find the partial derivatives. So I want to do the partial of f with respect to x and the partial of f with respect to y of f of x comma y equals x squared y cubed. So then let's start with the partial of f with respect to x. Now you're acting as though y is a constant. So here is some number times x squared. So you're simply going to get 2x and then just leave the y alone. And now if I want the partial with respect to y, I'm going to treat x as a constant. And so this time, the derivative of y is going to be 3y squared, but the x squared is left untouched. So I'll get 3x squared y squared. So that you really don't need a lot more. You don't really need much more than that to do the problems we're going to do in this section. So let's solve one of these things. Solve. We have sine of y minus y sine of x dx plus cosine of x plus cosine x cosine of y minus y times dx, and that's equal to 0. So remember, our answer, the answer will be it'll look something like f of xy equals a constant, because ultimately I'm just going to integrate through if I can integrate through. And what we have to do is to determine when can I integrate through like I did in the first example. And here's how you know. I'm going to think of this as m dx plus n dy. That equals 0. Now what I'm going to do is take the derivative of m with respect to y. So I'm doing it opposite the variable that's there. So m sub y, I'm going to treat x as a constant, and the variable is y. So in particular, I'm going to get cosine of y minus 1 times sine of x. So cosine of y minus 1 times sine of x. Now I'll do the same thing for n, but I'm going to take the derivative with respect to x. So that way I'll get a negative sine of x plus 1 times cosine of y and the derivative of y with respect to x is 0. So you can see I have m sub x equals n, well, that's m sub y, equals n sub x. That is the crucial part. This thing right here, if that's true, then I know that I have a solution. I'll be able to go and integrate directly back here. Let's go ahead and do that. So I'm going to just integrate all the way through. And let's start with the portion dealing with the first half. I'll have the integral sine of y minus y sine of x dx. And this is with respect to x now, so anything involving y is a constant. So I will just get here x times sine of y. And here, the y is a constant. I'll have minus y times negative cosine of x. So I get plus y times cosine of x. And don't forget to attach the c sub y. There may be a function of y alone that pops out as a result of this integration. Secondly, I'll go back to this guy here, and I will integrate cosine of x plus x cosine of y minus y times dx. And that will be, let's see, with respect to y, so I'll get y cosine of x. And then I'll have plus x times, let me see, oh, this is with respect to x to y. So I'll say it again, y cosine of x plus x times sine of y minus y squared over 2. Now what you want to do is locate the parts that are functions of just x, just y, and those that are a function of both of them. If you look here, this x sine of y plus y cosine of x appears in both. So that's part of my answer. So my solution, or my answer, it's going to look like this. This is the part that has x and y both together, and they couldn't be stripped apart. So I have x sine of y plus y cosine of x. Now, the c of y is easy to see. It's the thing that's a function of only y alone. That's the negative y squared over 2. So there's my cy right there. Now, if you notice, there's nothing left over. That means that c of x was 0. But now the other side is easy. Remember, we were originally starting with a differential equal to 0. So when you undifferential, it's going to equal just a constant. So let's go back to the central idea. Is this. If I take the differential of xy, that will be the partial of f with respect to x times dx plus the partial of f with respect to y dy. And all we're trying to do to solve this thing is integrate to go backwards. Remember, this thing is equal to 0. So if I integrate to go backwards, I'm going to integrate this, and that's going to equal the integral of partial of f, partial of x, dx. Break this thing up. Partial of f, partial of y, dy. And the other side, since it's the differential of something equals 0, we know that that thing is just a constant, in the real sense of a constant, not x or y. So now these are the things that we have to solve. I'm guaranteed to get my f back only if this thing here and this thing here cooperate with me. These two things will cooperate I'm just going to use that word, will cooperate, that means they will give me the same, both of these will give me the same function of two variables in both cases, so long as this piece that in front of the dx and this piece in front of the dy came from the same f. And the only way I can ensure that is if I take the partial with respect to y of partial of f with respect to x, and that's the same as the partial with respect to x, partial of f with respect to y. In other words, these are second derivatives, it turns out to be. The deal is, if this equals this, then when I go back and integrate, no matter how I integrate, I can flip the order of integrations and work my way back to the same x. So what we need, when I call this, what we're going to have is slightly similar. We're hoping the format is of this. So in order to hope that that format's true, we're going to start with an equation like this. That's going to equal 0. Now we have no inclination that this m and this n came from the same f. There's no guarantee of that, unless when I take the derivative of m with respect to y, different from that, that's this part right here. First with respect to x, hopefully that was already done with respect to x, and then with respect to y. If that equals this over here, first with respect to y, then with respect to x. So if those two things are the same. In other words, the second derivative, what they call a mixed derivative, partial of f with respect to x, then y, partial of f with respect to y, then x. If that's the same, then I can proceed backward because all the integrals are going to work out for me. Are equations that I've done before. If this is true, you know that you can find a solution. Now I want you to note, as far as I know, my method of solution is not found in any textbook. That means, I guess I take pride in the fact that I alone solve these particular equations in the way that I do. I think it's a lot easier than the book. If you want to take a look at the book's version, their solution is equivalent, but to me it's more cumbersome than what I'm doing, I think, at least. Let me do another example to illustrate. So now we've got some of the theory out of the way. Let's go ahead and just solve one of these things and see how it works. So I'll start with 1 plus 3 over y plus x times dy over dx plus y equals 3 over x minus 1. Now the first thing you need to do is to make sure that you get it in the format that we've been doing with all the other ones. So in particular, I'm going to multiply through by dx. So I have 1 plus 3 over y plus x dy plus y dx equals 3 over x minus 1 times dx. And then I'm going to get everything to one side and have it set equal to 0 like we're supposed to. So I'll have 1, I think I made a mistake actually in the problem. Let me make sure, let me fix it. You can see that they have to have a sort of symmetry for them to even possibly have a solution. Now when I bring everything to the left side, I'm going to have everything with respect to x over there. So plus y minus 3 over x plus 1 dx equals 0. Now I don't care about the order of them. I just know that my m's are attached to the dx. There's my m. And my n is attached to the dy. And when you do your test, you know that I need to take m with respect to y because it's attached to the dx. I will not have a mixed partial if I don't. So I'll have to do m sub y if I take that derivative, the y becomes 1, the negative 3 over x disappears, and so does the 1. And then n sub x, you can probably tell this is going to work out because of symmetry, but once again, with respect to x, I know I do that because it's attached to the dy. You need mixed partials. Derivative of x is 1, the rest of that stuff is 0. So I know I'm going to be able to get a solution now. So what I'm going to do is just integrate each of these pieces individually and then compare my answers. So we'll start with the integral of 1 minus 3 over y plus x dy. And this time everything's with respect to y, so I'll get a y minus 3 ln absolute y plus xy. And then I'm going to get a constant that might be a function of x. Similarly, I'm going to work the other one. I'll have y minus 3 over x plus 1 dx, and that will equal xy minus 3 ln absolute value of x plus a constant that may be a function of y. Now all I got to do is look for the things that have x and y together, and that forms part of my answer. So I see I've got an xy here, an xy here, and that's the only piece of each of these things that has x and y's together. So part of my answer will be xy. Remember, that's the thing that appears twice when you go to integrate the exact equation. So I'll have my xy. Now let's see if I can locate my c of x. Cx will be anything that involves x and x alone, and that's all of this stuff here. So I'll have negative 3 ln absolute x plus x. And how about my cy? That's all this stuff here. You can see the symmetry now very well. Cy is all that stuff. So I get plus y minus 3 ln absolute value of y. And that, as we know, is equal to a constant. So you can leave it like this. I'm perfectly happy with that. I, being the instructor, will go ahead and combine my ln's. And I'll get xy plus x plus y minus 3 ln absolute xy equals a constant. For my next example, we have 1 over 1 plus y squared plus cosine of x minus 2xy dy over dx equals y times y plus a sine of x, and that's all there is to it. So I need to I need to put this in a format that's like our other ones. So the first thing I'm going to have to do is multiply through by dx. So I have 1 over 1 plus y squared plus cosine of x minus 2xy. So that'd be dy. Now when I multiply by dx, I'm really supposed to bring everything to one side and have it set equal to 0. So it's going to look like minus y times y plus a sine of x dx. And that's equal to 0. So this portion, including the negative, this piece right here is my m. So let me go ahead and put that. And all of this stuff, of course, will be my n. Let's do n with respect to x. Remember, it's the opposite of the one that's there. So this piece here, since it has y alone, will disappear. Cosine of x will become negative sine of x. And then negative 2xy will become negative 2y. Now m, with respect to y, now it might be easier, as far as differentiation is concerned, to think of m equal to negative y squared minus y sine of x. So then when I take the derivative with respect to y, I'll get negative 2y. And then here, I'll get negative sine of x. So we can see I get the same thing for both pieces. N sub x equals m sub y. So I've got that. Now I can go and just integrate and see what happens. So I'll integrate the first piece. I'll have 1 over 1 plus y squared plus cosine of x minus 2xy dy. And when I integrate, hopefully you remember that 1 over 1 plus y squared is arctangent of y. Cosine of x, so it's like a constant in this world, so I'll have plus y cosine of x. This will be the portion that involves both y and x that you can't split apart. And then finally, I'll get a y squared over 2. It'll cancel out the 2, and I'll get negative xy squared plus a constant in x. For the other piece, let's see what I had again. I have, it may or may not be easier to leave it in that format. I guess I will. Let's go ahead and plug that one in. I'll probably put the negative out front, so I'll have negative y squared plus y sine of x dx. And so I'll get negative y squared x. And then I'll leave all this. I have negative sine x. The integral of negative sine x is cosine of x. So plus y cosine of x. And then plus a c sub y. So let's see if we can find all of our parts. Arctangent of y has only y alone. I should see a y cosine of x in both pieces and an x squared y in both pieces, xy squared. So this part right here is the same as this part right here. So my answer is going to be negative xy squared plus y cosine of x. Now let me see if I can find cx and cy. I see the cy is arctangent of y. The cx, though, must be 0. So, and that's equal to a constant. For the next example, suppose you have an initial value of y of 0 equals 1 in the previous example. So if you're given that, now solve for the, I guess solve the equation for the constant. So solve the equation now. I guess we'll say that. So we've already done the hard part. It's now just plugging in x equals 0 and y equals 1. So we have negative when x is 0, so we're going to have 0 times 1 squared plus 1 times cosine of 0 plus arctangent of 1, and that will equal a constant. Let's see, the 0 times 1 squared goes away, but the 1 times cosine of 0, well, that's 1, and the arctangent of 1 is pi over 4. So that equals the constant. Anyway, so our completed solution then would look like this. Negative xy squared plus y cosine of x plus arctangent of y would equal 1 plus pi over 4. So initial values, really, those are very simple to do. That's like the easiest part of the problem. If the equation is not exact, then All right, if the equation is not exact, say we have m dx plus n dy equals a 0, but m sub y does not equal n sub x. We're not completely out. We still have a shot at this. What we can try is we might be able to find an integrating factor let's call it mu, such that if we multiply the whole equation, so if I multiply everything by mu, an integrating factor mu, such that all this is still the same thing, but I'll have instead mu m dx plus mu n dy equals 0 is exact. So I'm looking for an integrating factor to make this exact. And mu is probably going to be a function involving x, y also. So what do we need to do then? If this is going to be exact, then I need to take mu m, take the derivative of this with respect to y. And that needs to be the same as mu n with respect to x. If that's the case, well, now this sub y and this sub x are just derivatives. So really what I'm talking about is taking this derivative here with respect to y. So in other words, the partial of mu m with respect to y. Use a product rule because u times m is a product. So I'll have the derivative with respect to y of mu. So I'll have the partial of mu with respect to y, leaving m alone, plus the partial of m with respect to y, leaving mu alone. And if I do the other one with respect to x, this mu n, so the partial of mu n with respect to x will equal the partial with respect to x of mu times n plus the partial of, this time what is it, n with respect to x, leaving mu alone. Now these two things need to be equal to each other. So let's set them equal to each other. So I'll have d mu over dy m plus dm over dy mu equals dm over dx n plus dn over dx mu. Let me soften this notation up a little bit. For this mu is the thing that we're trying to find. I'm going to change my dm over dy into the things we've been doing. So I have partial of mu with respect to y times m plus the partial, this right here we were calling m sub y times mu. That equals, that's supposed to be a mu there. Mu. My mu's got a little out of hand. So I have the partial of mu with respect to x, n, plus the partial of n with respect to x, which is called n sub x, times mu. These two things have to be equal to each other. So what I'm going to do is take the mu's to one side and take the other stuff to the other side. So what are we going to have here? I'll have the partial of mu all over y times m minus the partial of mu over the partial of x n equals mu times n sub x minus m sub y. Recall, when we do integrating factors, we're going to do something like this. Now the question is, can I integrate this mu if it's of multiple variables? Well, no, you're going to run into the same problems we had before. So I only want to use mu if it's a function of only x or a function of only y. If this occurs, then one of these two will be the thing that I multiply everything through by. This will be my integrating factor, in fact. So, what we need, in order to have a chance, we need mu to be a function only of x or only of y, because this integration, like I said, we can only do these integrations if it's in one variable. So let's start with, so if mu equals mu of x is a function of only x, then let's go back to the equation I had up here. All right, if it's a function of only x, then what happens here? Well, if it's a function of only x, I don't even need these squiggly things. The equation becomes d mu over dy m minus d mu over dx n equals mu times n sub x minus m sub y. So what do we have then? D mu, if it's a function of only x, then d mu over dy is 0. So I have 0 minus, I'm going to call it mu prime of x. Times n will equal mu times n sub x minus m sub y. Divide through by n and multiply through by -1 to get mu prime of x equals mu times, let me see, m sub y minus n sub x all over n. So now if mu prime of x is to be a function only of x, this mu of is a function only of x, this stuff here would have to be a function of x. So m sub y minus n sub x over n is a function of only x. Then I can take e to that dx. On the other hand, similarly, mu could be a function of only y, and let me write down what we'd have. If mu were a function only of y, then this d mu over dx would have been 0. I wouldn't have had to divide by, or I wouldn't have had to multiply through by the -1 in this equation. This would have been my mu prime. I would have mu prime of y times m would equal n sub x minus m sub y times mu, and then I would divide by the m, and I would require n sub x minus m sub y all over m is a function only of y. If either one of these cases happen, then I will be able to work with this thing and create for me a differential equation which is solvable. Let's do an example with that. So I believe this is example 6. I could be wrong. I think I may have lost track somewhere here, but let's do example 6. Let's say it's example 6. And I go to solve the equation. I have yx plus y squared plus y times dx plus x plus 2y dy equals 0. So first, let me check to make sure it's not exact. That's what this example is supposed to be. So the stuff in front of dx is my m. So my m sub x is going to equal, all the y's are going to disappear. The solo y's are all going to, sorry, I'm supposed to be doing y's anyways here. Anything involving just x will disappear, but there's nothing like that. The yx will become x. Y squared plus y will become 2y plus 1. N sub x will be 1. So we see that m sub y does not equal n sub x. So I'm going to look at both of these things and see if either one of them gives me a function of only x or function of only y. We've already taken the derivatives that I need. I just need to divide over n or over m. So start with the first one, m sub y minus nx. So m sub y minus nx all over, what was it, n. That equals, so I'm going to have x plus 2y plus 1 minus 1 all over, and n is x plus 2y. Well, this is nice. That's going to equal 1, and that's a function of, that is a function of only x. Constants will work. If I check, so this one will work. Let me check the other one, just to be on the complete side. So here I'll do nx minus m sub y all over m. So where's nx will be 1 minus m sub y will be x plus 2y plus 1 all over m will be x plus 2y plus 1. And I can tell this is not going to work. So I'm going to have 1 minus, well, the 1's will cancel. And we'll end up with negative x minus 2y all over x plus 2y plus 1. And you can see this one won't work. All right, so what is our integrating factor? Our I dot f is given by e to this power. And I'll put that up there. You can use this. It depends on whichever one works out for us. M sub y minus m sub x all over n. This is supposed to be a function of only x. That equals e to the integral of 1 dx. This was the important part, why it had to be a function of x alone, so that I can do this integration, e to the x. So now come back to the original equation. I'm going to multiply everything through by e to the x. So I'm going to get e to the x times yx plus y squared plus y times dx plus e to the x times x plus 2y dy equals 0. Now, this is now exact. Because if I take this derivative with respect to y, the e to the x is a constant. This right here now, this is my new m, if you will. This guy right here is my new n. It's like we're starting a brand new problem. And then if I do m sub y, the e to the x is not important. That will just act as a constant being multiplied. I'll get the same things I did before. I'll get 2y plus 1. I'll get x plus 2y plus 1. And then over here, if I do n sub x, well, here, I think I'm going to have to rewrite n as x e to the x plus 2y e to the x. The reason why I'm doing that is because I'm going to have to use a product rule on the x e to the x part. So I get 1 times e to the x plus x times e to the x plus 2y e to the x. Let me strip out that e to the x to show you that they're going to be the same. 1 plus x plus 2y. So with some manipulation, we got this to work. I am going to leave now the solution to you, just integrate straight across, and the answer that you should get when all is said and done will be as simple as this. E to the x times xy plus y squared equals a constant.